Imagine one of the hottest afternoons of a Dubai summer. The glass towers are still standing perfectly upright. The artificial islands remain perfectly shaped against the coast. Dubai International Airport continues clearing flights without interruption, and the famous skyline has not disappeared. But beneath the surface, the invisible system responsible for continuously removing heat begins to fall behind. Within hours, the question inside these buildings changes from whether Dubai is comfortable to how much of the modern city can actually continue operating normally. The answer depends entirely on cooling. Yet, Dubai's cooling infrastructure is not currently collapsing. In fact, it is expanding faster than almost anywhere else on Earth, which raises a strange contradiction. If the system works so well, why does Dubai keep needing more of it? For most of the world, air conditioning is treated as a household appliance. It is a luxury that makes a hot afternoon more tolerable for a few hours. But that definition does not apply to this environment. During extreme summer conditions, cooling in Dubai ceases to be just about personal comfort. It becomes the baseline infrastructure required to sustain the entire indoor economy. Every glass high-rise apartment, luxury hotel, indoor mall and restaurant relies on the continuous mechanical extraction of heat. Without it, the buildings themselves do not physically collapse into the sand. But their ability to function as designed begins to rapidly degrade. This is especially true during the summer peak load window, typically between 12 p.m. and 6 p.m. During these hours, the outdoor temperature creates enormous thermal pressure on millions of square meters of enclosed indoor space. The heat does not simply stay outside the walls. It transfers through glass facades, concrete barriers, and ventilation systems, relentlessly pushing internal temperatures higher. To maintain operations, the city must constantly push that heat back out into the atmosphere. This requires a massive technological layer placed directly between the desert climate and everyday urban life. But managing this thermal pressure across an entire global hub requires more than just thousands of individual window units. It requires an industrial-scale solution. If so much of modern Dubai is effectively built on the assumption of controlled indoor temperatures, how does a city this large actually supply it? To find the answer, you have to look away from the skyline and look underground. Take Palm Jumeirah, one of the most recognizable coastal developments on the planet. Above ground, visitors see pristine beaches, waterfront restaurants, high-end resorts, and uninterrupted luxury. It looks like a completely self-contained vacation environment. But beneath the roads and the landscaping, there is a massive, highly pressurized circulatory system. Instead of individual air conditioning units struggling on every balcony, many of these luxury environments are connected directly to district cooling. This means massive centralized plants generate highly chilled water. High-capacity industrial pumps then push that water through insulated underground pipes directly into the surrounding buildings. The buildings extract the cooling to chill their internal air, and the warmer water returns to the plant to be cooled all over again. It is a continuous, closed-loop cycle of heat removal operating constantly beneath the streets. Recently, Empower, Dubai's largest district cooling provider, signed an agreement to supply the Palm Gateway development with approximately 9,470 refrigeration tons of district cooling capacity. To put that into perspective, a typical home air conditioner might use 3 or 4 tons. This single development requires the equivalent of thousands of homes, entirely supplied by chilled water flowing unseen below ground. Some of Dubai's most spectacular environments depend entirely on an industrial system that almost no visitor ever sees or thinks about. But Palm Jumeirah only proves that this invisible infrastructure exists. To understand how massive it has really become, you have to look at the commercial center of the city. Business Bay is one of the densest commercial and residential districts in Dubai. It is a concentrated forest of glass towers reflecting the intense desert sun. Cooling one of these towers is a significant engineering challenge. Cooling dozens of them requires a highly synchronized network, but cooling an entire district requires urban infrastructure on the scale of a major public utility. Currently, Empower's Business Bay network serves approximately 201 individual buildings. Together, they represent a connected capacity of roughly 276,545 refrigeration tons. And the system is still aggressively growing. A new district cooling plant is currently being designed for the area, capable of adding up to 44,000 more tons of capacity. This transforms air conditioning from a simple mechanical feature into a critical urban artery. When you zoom out from Business Bay to look at the wider city, the true scale of the cooling operation becomes clear. By the end of 2025, Empower reported operating roughly 90 district cooling plants across Dubai. These plants pump chilled water through more than 430 kilometers of underground distribution pipelines. That is enough pipe to stretch across entire countries, entirely dedicated to moving cold water through the desert. This single network serves 1,747 buildings, with a total contracted capacity of nearly 2 million refrigeration tons. One building requires a chiller. A rapidly expanding city requires an interconnected underground grid spanning hundreds of kilometers. But there is a catch to building an infrastructure network this massive. Every pump, every chiller, and every kilometer of pipe is designed to handle the most extreme thermal conditions. And all of that infrastructure faces its absolute largest demand at exactly the same time. As the morning ends on a midsummer day, the pressure on the system begins to escalate. By 11 a.m., the intense solar radiation is baking the concrete and heating the millions of square meters of glass wrapped around the city. Inside, building management systems detect the rising internal temperatures and demand more chilled water to compensate. By 12 p.m., the city enters its peak load window. Cooling demand rises sharply across every sector at once. By 2 p.m., the district cooling plants, the underground pumps, and the conventional air conditioning systems are working at maximum intensity. They are forced to reject massive amounts of indoor heat into outdoor air that is already extremely hot. By 4 p.m., large portions of the entire city are pulling heavy cooling loads simultaneously. This thermal pressure translates directly into electrical pressure. To move all that water and run all those chillers, the system requires an enormous amount of power. In 2025, Dubai's Electricity and Water Authority, DEWA, reported that annual peak power demand reached approximately 11.39 gigawatts. That was an increase of nearly 6% from the previous year. A large portion of that electricity generation during peak hours goes straight into air conditioning and cooling infrastructure. The chain of events is incredibly rigid. A hotter afternoon creates more cooling demand, which requires more electricity, pushing the overall system load higher. The entire operating environment of modern Dubai is balanced on this synchronized daily peak, which forces the obvious question. If the city requires this much power just to fight off the afternoon heat, what happens when Dubai finally reaches the limit? The obvious disaster story assumes that the electrical grid is currently sitting on the verge of total collapse. It is easy to imagine that one hot afternoon will simply overload the system and plunge the city into a permanent blackout. But the evidence does not support that narrative. By the end of 2025, DEWA reported an installed generation capacity of roughly 17,979 megawatts. While installed capacity is not the exact same thing as continuously available operating reserve, the margin between peak demand and maximum generation capability remains substantial. More importantly, the network actually delivers on its promises. In 2025, DEWA reported an exceptionally low 0.82 customer minutes lost annually per customer. By its own published metrics, Dubai's power system is operating with highly stable reliability. If the power supply is not collapsing and the cooling plants are continuously running, then the most popular apocalyptic scenario is wrong. An immediate, citywide blackout is not the actual problem. The real threat is something much quieter and far more structural. Collapse is not the real story here. The real threat is the cooling race. Dubai did not solve the extreme heat by changing the climate outside. It solved it by building an enormous technological shield between the city and the sun. But the more successful that shield becomes, the more the city grows behind it. And growth requires the city to constantly keep solving the exact same problem, just on a much larger scale. Dubai has not stopped building its massive cooling infrastructure. It is actively expanding it in almost every direction. This is not limited to a few legacy projects or iconic tourist destinations. The network is continuously stretching into new residential and commercial zones across the map. Cooling pipes are being laid beneath the Deira waterfront development. Chilled water is being pumped into Jumeirah village and Al Sufu. New capacity is being engineered for Dubai Science Park, while Business Bay continues to add massive connections. The pattern is relentless. A new glass skyscraper requires a new chiller connection. A newly zoned district requires a massive expansion of the underground pipeline network. An influx of new residents translates into permanent, non-negotiable thermal demand. Once a building is connected to the grid, its cooling requirement becomes a permanent baseline that must be met every single summer. This creates an unending cycle of urban engineering. To sustain economic growth, developers must build more indoor spaces. To keep those indoor spaces functional during a brutal summer, the city must lock in more cooling capacity. The entire urban expansion strategy operates on the assumption that the invisible infrastructure below ground will always be able to keep up with the steel and concrete rising above it. Dubai solved the heat by building cooling infrastructure, and now its future depends entirely on that solution never falling behind. But if Dubai is becoming increasingly dependent on this massive, interconnected mechanical system, it raises an important engineering question. Why use centralized district cooling at all? The answer comes down to pure efficiency. When cooling demand reaches this magnitude, strapping individual air conditioning units to every apartment window becomes a logistical and electrical nightmare. A centralized district cooling plant changes the equation. It chills a massive volume of water in one centralized location. Industrial pumps move that chilled water through the underground network to multiple buildings simultaneously. The buildings extract the cooling, and the warmer water returns to the plant to complete the continuous cycle. Because this process is centralized, it operates at a scale that individual building chillers simply cannot match. Empower states that its district cooling solutions can use substantially less energy than conventional cooling systems in its direct comparisons. But this engineering success introduces a fascinating twist. The high efficiency of district cooling does not weaken the story of Dubai's dependency on it. It actually strengthens it. Dubai needs highly efficient cooling precisely because its overall cooling demand is so massive. Efficiency reduces the amount of electricity required to provide a single refrigeration ton, but it does not eliminate the city's fundamental need for the cooling itself. Every time a new district is designed around the reliable flow of centralized chilled water, it adds another permanent obligation to the network. Every new building designed around reliable mechanical cooling adds another long-term obligation to the system. This turns an engineering triumph into a deep structural dependency. To understand the weight of that dependency, you have to look away from the machinery and look at the people living inside the system. This is not a story about basic human survival in the desert. The argument is not that people would instantly die if the air conditioning was temporarily switched off. The true stakes are entirely operational. Think about the thousands of tourists standing inside massive luxury hotels. Look at the families living in high-rise apartments, the employees working inside floor-to-ceiling glass towers, and the shoppers circulating through vast indoor leisure environments. Every single one of these spaces has been architecturally and economically designed around a specific expectation. They assume that reliable mechanical cooling will always be available to push the internal heat back out. This reveals the core paradox of modern Dubai. The better the city becomes at protecting itself from its harsh climate, the more of the city can be built as though that climate no longer matters. Entire economic sectors are now heavily decoupled from the actual weather outside. But that decoupling is fragile. It only exists as long as the pumps keep running, the water stays chilled, and the pipes remain pressurized. Without continuous cooling, the economic value of these spaces drops drastically. How many of Dubai's most famous commercial spaces would still function the exact same way if their indoor temperatures suddenly began following the weather outside? The answer is almost none. The modern urban environment is practically an artificial envelope, and that makes cooling an anchor system. It is a piece of infrastructure that simply cannot fail, because so many other essential networks depend on it. But cooling does not stand entirely on its own. It is deeply woven into a web of other essential systems that must also keep working to maintain the city. Cooling sits inside a network. Industrial pumps require continuous power, central plants require massive amounts of water, and high-rise buildings require uninterrupted internal circulation. According to the International Energy Agency, cooling currently accounts for nearly half of peak electricity demand across the broader Middle East and North Africa region. The agency expects cooling to remain the largest driver of electricity demand growth in the region through the next decade. While this is regional data, it perfectly illustrates the scale of the pressure. Cooling is not just one isolated mechanical process. It sits inside a complex network of power generation and urban infrastructure. If any part of that network faces severe strain, the pressure transfers directly back to the city's cooling capacity. To understand the future stakes of this dependency, you have to look at how fast the city plans to grow. Under the official Dubai 2040 Urban Master Plan, the resident population is projected to rise dramatically. It is expected to grow from approximately 3.3 million people in 2020 to roughly 5.8 million by 2040. Every additional resident translates into a permanent expansion of the urban footprint. More residents mean more development, which requires more high-rise apartments, more commercial floor space, and a massive increase in enclosed indoor environments. All of this new architectural volume will face the same extreme summer heat, and all of it will require continuous, reliable temperature control. While modern buildings are designed to be far more energy efficient, better efficiency only slows the rate of demand growth. It does not eliminate the fundamental need to remove heat. A denser city with millions of additional residents simply requires a larger, more powerful infrastructure network to survive the summer. This creates a relentless urban race against the climate. Dubai has repeatedly demonstrated that it can successfully cool the enormous city it has built today. But the master plan introduces a much heavier long-term obligation. The pressure on the invisible grid below ground will only continue to multiply. What happens if the massive development of new districts outpaces the installation of new district cooling plants? Dubai has demonstrated that it can cool the city it has today. But what happens if, one day, the infrastructure fails to expand as quickly as the city above it? Consider a hypothetical stress test during the absolute peak of a midsummer heat wave. This is not a forecast that Dubai will inevitably experience this specific disaster. It is a way to look at how deeply the modern city relies on continuous mechanical control. Imagine it is 1 p.m. The cooling load across the city continues climbing as severe thermal pressure builds against millions of square meters of glass. At 2 p.m., a hypothetical localized disruption occurs within a specific power or cooling distribution network. Perhaps certain chiller plants lose capacity, or underground pumps temporarily fail to maintain adequate water pressure. By 2:15 p.m., the affected buildings can no longer pull enough chilled water to fight off the relentless solar radiation. By 3 p.m., the enclosed indoor spaces gradually begin to warm. The heat does not instantly kill anyone, but by 4 p.m., building management systems are forced to actively manage rising internal temperatures and increasing operational pressure. Luxury hotels become uncomfortable, commercial offices lose productivity, and heavily glazed high-rises struggle to maintain a habitable baseline. Outside, nothing has physically collapsed. The iconic skyline is completely intact, the highways remain open, and the towers still look spectacular. But the artificial indoor environment separating the occupants from the extreme outdoor heat has fundamentally weakened. This answers the underlying question of the entire story. Would all of Dubai literally become biologically uninhabitable overnight without its cooling system? No. But in an extreme scenario, large portions of the modern city would become increasingly difficult to operate normally during extreme summer heat without reliable mechanical cooling. The economy relies on the illusion that the desert heat does not exist, and when the cooling system struggles, that illusion breaks. This reveals the great paradox of modern Dubai. The city did not defeat the extreme heat by altering the climate outside. It engineered a massive, highly efficient, and technologically advanced urban layer capable of functioning directly around it. The vast network of chilled water pipes, centralized plants, and industrial pumps is undeniably one of the greatest engineering successes in the region. But that exact success is what allows the modern city to grow so large and to become so deeply dependent on continuous technological intervention. Dubai's giant cooling infrastructure may be one of its greatest engineering successes, but it reveals something fundamental. Modern Dubai does not simply live in extreme heat. It continuously engineers its way around it. The most important question is not whether Dubai's cooling system is failing today. The published evidence shows a system that is expanding rapidly and operating with high reliability. The better question is whether Dubai can continue expanding the invisible infrastructure below the city exactly as fast as it expands the ambitions above it. Because if the cooling ever stops keeping pace, it is not just the indoor temperature that changes. The entire operational reality of the city is redefined. This video is for educational and analytical purposes, examining urban infrastructure and hypothetical stress scenarios based on available projections. It does not represent a prediction of imminent system failure and should not be used as a substitute for professional engineering advice. How far do you think a modern city can push the limits of environmental engineering? Let us know your thoughts in the comments below, and subscribe to see more investigations into the massive systems that keep our world running.